So, you want to find the roots of a quadratic polynomial. Good news! The method of completing the square always works. What makes that so, and what other information can we glean from this method? Let's find out with an example. We'll find the roots of 5x squared plus 10x minus 3. Before we can even start, we need to do some pre-processing. First, that 5 at the beginning has got to go. We can vanquish it by dividing everything by 5. This new, easier to solve equation codes for a different parabola, but with the same roots. The second thing we need to do is to find a new home for that third term. We'll move it over to the right-hand side of the equation. Remember that when it crosses the floor, that is the equal sign, it changes its allegiance, the sign. Thus, it becomes positive 3/5. This is what we want. The part on the left is the square that needs completing. It will always have the form x squared plus bx, where b can be any number. The number on the right can be anything, even 0. This diagram represents x squared plus 2x as the area of a rectangle. One side has a width of x, and the other has a length of x plus 2. We've divided the rectangle so that it consists of a square and a smaller rectangle. Next, we slice the smaller rectangle, the one with the area of 2x, down the center. We move half of the rectangle to the top of the diagram. The clear portion of the diagram has the same area as the previous diagram. However, it is now a square with a bite missing out of the top right corner. We've shaded in the bite to complete that square. The square has a side of width x plus 1. Thus, its area is x plus 1 all squared. This area, less the shaded portion of area 1 squared, is the area of the original rectangle. We want the x plus 1 all squared on its own, so we move the negative 1 squared to the right. It becomes plus 1 squared, which is 1. To remove the parentheses, we take the square root of both sides. Both positive and negative solutions will work. Finally, we slide the plus 1 over to the right-hand side of the equation. This leaves us with the two roots. X equals negative 1 plus or minus 2 times the square root of 2/5. This format shows us that the vertical line down the center of the curve is at x equals negative 1. The roots are 2 times the square root of 2/5 to the left and the right of this line. We can generalize this process for any quadratic. Here, a, b, and c can be any numbers. As before, we need to remove the first coefficient. We divide everything by a. Next, we move the third term to the right and change its sign. The general diagram now looks like this. The only thing different is the coefficient before the x. When we split the smaller rectangle as before, we cut that coefficient in half. Our equation now takes the form area of the square less the shaded bit equals the number on the right. As before, we move the second term, the one without the x, to the right, changing its sign. Then we take the square root of both sides. Once we move the second term to the right, isolating the x, we have our roots. we need only to clean up the bit inside the square root. The denominator inside the square root is a perfect square. Thus, it will become 2a. Putting everything together, we arrive at the quadratic formula we all know and love. Where in the first example, -1 revealed the vertical axis of symmetry, in the general equation, -b over 2a plays that role. Using the quadratic formula is the same as completing the square on autopilot.